Welcome everybody to the Propeller 2 live forum. Today we are with JonnyMac talking about asynchronous serial communication. I see a lot of familiar faces. It's a good thing. Before John starts, I will be, actually as he starts, I'll paste a few links into the chat so you can go get today's code from the forums. In 2 weeks as well, keep your eyes open for the XB presentation. So February 24th, 3 p.m. This is an hour earlier than they were around Christmas time. And I'll also include a few links for XB modules, the Series 3 module, and the adapter boards that go with it. And then in 4 weeks, which will actually arrive sooner than we think, stepper motors. And we'll be using the Polarity driver that's featured here, the A4988, the black board they call it, which supports higher current, and then just a small 1.5 to 2 amp stepper motor. And you can have a couple of these handy to give yourself some freedom. So that's going to be a lot of fun. John, I am ready to pass it over to you.
Okay.
And I'll go retrieve links now and paste them into the chat.
I did. The very first post in the chat is the link to
Perfect.
file the thing with the code. Yeah.
John, I'm not seeing that in the chat.
You may have arrived late, so I'll get it.
Okay.
Okay. Yeah.
Seems like you only see the chats that arrive after you've arrived.
Oh, that makes sense. Yeah, sorry, gang. I tried to get them up a little earlier, but I decided, oh, let's throw in one more demo. And then, of course, it didn't play nice with Flex Prop, so I had to rewrite it. So but it's okay because it points out a couple of traps that we have to deal with from time to time. So are we ready to go, Ken?
Good to go.
Okay, all right. Hello, everybody. I will just, oh, I guess I should probably share my screen too, right?
And if we need a break, we could just watch the CNC machines run.
Yeah. Jim seems to have a lot going on there. Okay. Can you see my PowerPoint presentation?
It's looking good.
Okay. All right. So we'll go through here. I'm going to see if I can get it to run in, that's not in slide mode, and that will make it a little nicer. Okay. Today we're going to talk about serial, or, technically asynchronous serial. And, it's funny, this is one of those things that we tend to take for granted because we use it so often. And really, we should have done this one first because we've been using it since the very first presentation, whether people understood that or not. I think probably most people did. But, first let's talk about serial just to make sure we're all in line with the definition. That means we're transmitting information, but just one bit at a time. So in a serial manner, versus parallel, which we send out multiple bits simultaneously. So those, and I'm picking on him because his picture's right below mine on the window. Francis, guys our age, had computers that had parallel ports on them and old school serial ports that were at a fixed address. Many young people have never had that joyful experience. But the serial allows us to transmit data a little more slowly than with parallel, but we're using fewer I/O pins. So with asynchronous serial, remember we've done this definition several times, asynchronous means there's no clock. And so that means that the parties involved in the transmission have to have an agreement. But for asynchronous serial, we use it often for point-to-point things. And I'll give you an example. In the early days of the basic stamps, there were serial LCDs kind of came into life. And that was the basic stamp sending messages through serial mode to an LCD to display on it. We did that in a previous tutorial, but we used instead of straight asynchronous serial, we used I2C, another type of serial mechanism. We can also do multi-point stuff. That's something I get involved in a lot with DMX and other RS-45 things. So I'm going to talk about that a little bit. And certainly when we get to the XP stuff in a couple of weeks, that can be point-to-point or point-to-multi-point. And here we're talking about the data mostly. Now, the things we're going to do frequently will be over a wired system, but as I just pointed out, XP is wireless serial. And now there are some complicated and sophisticated protocols running underneath. The nice thing is they are running underneath and they're kind of abstracted for us. So there, for example, is a mode in the XP devices where you can configure them such that one end looks like it's talking to the other end through a wire. It has no knowledge that there are these sophisticated devices in between. That's called transparent mode. Another mode, for those of you that might have been, early and heard me referring to laser tag, I've worked with a laser tag company, one of my clients, and we use XPs in that system to, for example, I was saying, Ken, if you shoot me, what happens is my radio knows so the victim device knows the system address of the victor device because it's encoded in the IR bullet packet. And with that knowledge, the victim can send a coded message to a specific XB, which is the shooter, and say, hey, you got me. Because if you're, 1,000 feet away, you can't always see things lighting up. So you get a radio message and you get this, excited voice coming out of your tagger that says, good hit, or that's a kill, or, fun stuff like that. Anyway, with serial, we're going to do half and full duplex. Half duplex is one side at a time talks. Full duplex means both sides can be talking simultaneously. We can send data while receiving data. Now, with the P2, we have lots of opportunities for generating and receiving serial data, and some apply to both. Some, and as far as half and full duplex, some are not so good for the other. So we'll see that. And I made a mention a moment ago that in the serial communication scheme, the endpoints have to agree on their transmission speed. This is called baud. It is measured in bits per second. And so, for example, in all of our demo programs, there's a constant called BR_term, and it's presently set to 230,400. So that's 230,400 bits per second. Now, pop quiz. How many bytes per second is that? Bueller? Bueller?
Be at least 1/8 and 1/8.
Well, so technically it's a trick question.
It's 10s or 11s.
Well, exactly. So Stephen knows where I'm going with this. We're going to see as we're looking at the construction of serial data, we have more than just the data bits in the in each byte of the packet. We have what's called a start bit, which says, hey, here we come. And then we have a resting period at the end of the data bits called a stop bit, which could be more than one stop bit. So we need to know how many stop bits, because we're always going to have at least one. We're going to have a start bit, then our data bits, and then a stop bit. So we have to know how many total bits in the transmitted byte in order to determine how many bytes per second we're transmitting. In bits per second, that's gives us the timing. Hey, when I'm talking through our discussion, I'm primarily talking about what we're going to generically call TTL serial. It's, propeller to another propeller, or propeller to a device like the PixieCam or other serial type devices. So they're going to be at the IO levels of the pins. Now there are two polarities that we talk about with serial. There's true mode, which is what's common, And in that case, when the transmit line is at rest, or it's idle, or what we call the mark state, it's at VDD, or in our case, it would be 3.3 volts. And when we get a start bit, which goes low in true mode, that's going to be 0 volts. So that's called true mode serial. There is also an inverted mode, which is the inversion of that. The mark state is low at 0, and the start bit or space bit goes high. And this, I think, yeah, it could be wrong, but this kind of came about, or it certainly was popularized by, again, those computers I was teasing Francis and myself about that we used to have that had old school 9-pin serial ports on them, because those ran at RS-232 voltage levels. And if you look here in the RS-232 voltage levels, the mark state was somewhere around the minus 12 to minus 15 volt level. And then the space state, or where the start bit was, went up to plus-ish 12 to 15 volts. Interestingly, microcontrollers have diodes built into their pins to protect them from over voltages. Now, that's all well and good, but you have to protect those diodes from overcurrent. So what we used to do in the old days, and some people still do it because I noticed that Lachlan mentioned this in the forums a couple of days ago, we would put, you know, roughly a 22K resistor in series with a serial port out of an old IBM PC, and then run that into, say, a basic stamp. And now we could get serial directly from the computer into the stamp. But because of the levels of RS-232, and what was happening there is that the one diode would just clamp the minimum voltage to roughly 0, and then the other diode would clamp the maximum voltage, which is where the start bit level was, at about 5 volts or so. Remember, that was a 5-volt device. So but it was inverted. So we had inverted serial, but you could have a serial port on your computer talking directly to a basic stamp. I did this with several projects, even a couple of commercial devices. It doesn't happen very often, but we will sometimes only use 7 of the bits in the byte for the actual data. And then as a way for kind of error detection, we'll use the 7th as we call a parity bit. And so there are odd and even parities. And the way that works is that bit 7 is going to be set to create either an odd number of bits in the entire byte, and that's in the data portion, or an even number. And you know, it's a little bit of extra work to do if you need that. I recently had a device that I had a parity requirement. So I had to count the ones in the P2. It's really easy. There's actually an instruction called ones that does that for us, and then add that bit. So you'll see, for example, 8N1. That's a very typical kind of descriptor of a serial byte, which is 8 data bits. There's no parity, so we're using all 8 of the data bits, and we have 1 stop bit. You might, for example, though, see 7E2. You know, it's an odd thing, but that's 7 data bits. We're using even parity, so that's where that other bit is going. And then we're going to have 2 stop bits. Okay, makes sense. It's pretty straightforward. Let's look. I think I have an image coming up next, so I'll have it in a second. On the P2, there are, like I said, as with any microcontroller, there are multiple ways to create and receive serial. You can, in fact, do it in spin. I was telling a friend the other night, I actually laughed out loud, which I frequently do with a spin. I mean, I am a giggling idiot living in Hollywood all by myself, so I'm easily entertained. But I was able to use old spin code that we've been using since the P1 to generate simple serial transactions. And I never tried higher than this, but it was able to run 230K baud using interpreted spin, you know, through the Propeller tool. running at 200 megahertz. Remember, the propeller will comfortably run up to 300, 320 megahertz. So we could get even faster baud rates. Now, that's really easy. I'm going to demonstrate it here just to show people, hey, how we construct a serial packet or byte rather and transmit it out or receive it in. But it's not very practical for real world use because RX is blocking. It's kind of, again, for those of you that have been around a while and use the basic stamp, you may remember that originally the sear in instruction was blocking. It would not let you move past until something came in. So that can create problems. And there's no buffering. You would end up having to stick it into a cog to do all that. Now you've kind of defeated the purpose of the simplicity. In assembly, it's also very easy and it can be much faster, of course, because we're using assembly. And then we can do things, since at that point we are going to use a cog, I'm sure. We can also do half duplex over one wire. And this is kind of common chip to chip kind of thing. I've done it a gajillion times with boards like the HC8. This is a P1 board, but EFX Tech makes this. And it has a little serial port on it that is designed to hook up to other propellers, and they talk to each other through a one-wire serial connection. So in that case, it is limited to half duplex because there's only one wire. So you're either sending a message or you're listening for a message. You can't do both at the same time over one wire. So I'll show that configuration. Finally, as far as generating serial on the P2, we now have Smartpins. So the Smartpins do the hard work of timing and transmitting or receiving and timing the bits. So they become the physical UARTs. And this means we can get really fast data rates. We can get weird bit numbers too, because we have within Smartpin the ability to deal with 32 bits. So you could have a non-8 bit number, and that really exists in the world. Some years ago, I was contracted to write a version of full duplex serial that dealt with 9-bit values because I think it was a soda machine industry uses a serial connection where they use 9-bit values, not 8-bit values. And that was not difficult to do. The fun thing with the propeller too, even certainly didn't have a Coke machine in my apartment, but I was able to write the driver because they really just wanted a transmitter, but the only way for me to test it was to write the receiver too. So I wrote the transmitter, wrote the receiver, ran them in separate cogs and watched them talking back and forth and gave them both to the client, and they went off and built a lot of product with it. So it's kind of neat. So with the Smartpins, they're very fast and we can do interesting things, but and remember, I come from a practical point of view. You can do anything given enough patience. I'm not a terribly patient guy. So I'm suggesting that Smartpins are not the best situation for half duplex because you'd have to reconfigure the pin on the fly. Not that you couldn't, you actually could, but I think that I wouldn't be bothered doing that. Okay, so here's the, an 8N1 serial byte. The top line is true mode. I'm trying to find my cursor. So this level here is at our 3.3 volt level. And so this is the mark level, or the idle state of the transmit pin. And then when we want to transmit a byte, it's actually very easy. Because we know what the baud rate is, we know how long each bit is. And even if we're synthesizing that in code with the propeller, it's very easy because we can look up the clock frequency, there's an instruction for it, and divide that by the baud rate. And that will give us, that'll go from our system clock, which is in ticks per second, to now ticks per bit. And we can use that as a timer. So in a serial byte, we have a start bit, which will take the serial line to the space state. In a true mode, that's going to go down to 0. We wait for the bit time, and then we're going to send out the bits, doing the same thing. We're just going to put the bit value on the transmit line, and we are going to go from the LSB in. end. So this is the LSB, the next bit, and this is the MSB of the value. Finally, when all those bits are sent out, we will return to the mark state or the idle state for at least 1 bit period. And the reason for that, if it's not apparent, is that we have to give the receiver time to take what we just sent it and put it away somewhere before another byte comes in. So that's, that's part of the reason for the stop bit. And in many systems, for example, I'm going to show you some DMX code because I do DMX a lot. And I use 2 stop bits there. It's not necessary, but that's what the DMX spec calls for, is a start, 8 data bits, and 2 stop bits. That gives the devices plenty of time to deal with the byte that just came in. And remember, the DMX spec, or if you don't know, it's been around a while. And I'm sure that things would work fine without it, but it does use 11 bits. Now, again, here's the inverted mode. So that's just, again, that's an electrical inversion. I just talked about transmitting. And before we get into code, I'll just show you, I made a note down here. So you'll see this says 1.5, 1, 1, 1, 1. This is bit periods. So when we're receiving, when we're a receiver, what we are going to do is watch for this.
What is Stemma QT? Stemma is an easy way to connect sensors.
Oh, sorry, that wasn't me.
Commercial.
When the start bit happens, what we're going to do is we're going to set a timer initially to 1.5 bits. This is one way to do it, because what that does is when that timer expires, we're now in the middle of the first bit. So we can, that's where we sample the line to see, what it is, and we grab that bit and put it away. And then we reset that timer to 1 bit period, and we do that for all the rest of the bits. The nice thing about this, you notice that we're sampling, attempting to sample anyway, in the middle of the bit. This gives us a little bit of wiggle. I think the number generally people like to accept, you'd like your baud rates to be within 2 or 3% accurate so that everything is on. Sometimes you get away with more than that. In fact, interestingly, if you look at some of the older XP devices, I'll have to look at the data on the new one, the baud rate generators inside them meant that they didn't actually hit the baud rate numbers they were being set to. They were hitting these funky numbers. And I remember when the guys at XP were telling us at the laser tag about that, and they said, this could be a problem, so you may want to use a slower data rate. I said, no, it's no problem. I can adjust the baud rate to the exact rate coming out of the XP or going into the XP, because of course we are not using hardware baud rate generation, traditional baud rate generators. So we can have any baud rate we want. I also did that. There is a motor device that some of you may be familiar with. That now the name just flew right out of my head. Darn, it's like a smart servo device that is on a little mini network. It too has odd baud rates.
Dynamixel?
Thank you, Roy. Yes, Dynamixels. In fact, I've written code for them for movie props for my friend Rick. He's used them in a couple of movies. There's since it went past with COVID, there's a Tom Hanks movie coming out where he's the last man in the world trying to build a robot to feed his dog after he dies. Those robots were built by Rick with Dynamixels that I helped Rick with code with. So watch for Tom Hanks being the guy about to die, teaching his robot to feed his dog. And anyway, the nice thing about the Propeller is that we can do odd baud rates with no problem at all. That makes things really solid. The first time I used Dynamixels in a prop kind of thing was with my friend Matt. And we were struggling a little bit. And then I remembered, I could do these tricks. And now suddenly it was a Terminator head. And then it started moving and animating really, really nicely. It was quite nice. But anyway, again, serial is very simple. We're going to have a start bit. We're going to send our data bits in order from LSB to MSB. Remember, if we are using parity, this bit, where I'm calling D7 here, that's going to be our parity bit. and then we'll have one or more stop bits. And there we go. Now this is the signaling, I guess. The transmission medium could be wire, could be radio, could be infrared, it doesn't matter. This is how we're sending the bits. Here's a real world example. I hooked up my little tiny $12 logic analyzer, sent out a byte. In this case, it's the byte, it's hex 73. Now remember, what I was just saying, we're sending the bits LSB to MSB. So we have to kind of read that backwards. Here's the stop bit here. So 7 would be 0, 1, 1, 1, right? So there it is, 0, 1, 1, 1, and then 3 would be 0, 0, 1, 1. So you can see the bits. And this is a true mode serial. So you see we're idling at the mark state, and here's our start bit. And from that, remember, everything is timed now. So that is the thing with asynchronous serial, both ends have to agree on their transmission rate, and then the receiver is watching for this edge to know when to start doing things. Now, that ability of sampling in the middle of bits that I was talking about, that helped some of the folks on the stream have probably used the SX controller back in the day, and we would do kind of interrupt driven serial generation. And what we would try to do is have our interrupt periods so that it was a multiple of at least 5 to 7 bit periods. That seemed to be sweet spot, that or higher. You don't want to have it be interrupting too much, or else you never get anything else done. And that would allow the generation and the receipt, because if you're not able to detect the start bit exactly when it came in, because it may already be in a start bit mode when you hit the interrupt, that amount of resolution gave you the ability to do that. So it's much nicer in the Propeller. Here's some really simple connection examples. This is full duplex. The dark line means we can be active. So we can transmit and we can receive at the same time. So for example, when we're using the terminal, we're not really doing it, but we can send and receive data simultaneously. We can also have a situation where we have 2 wires, but we have a half duplex device. So in this case, this is, for example, the PixieCam that Ken likes to put on his robots. It has 2 wires, but it is half duplex. So you have to send it a message and then you get a response. The PixieCam does not send without being prompted by the master controller. Here's that setup I talked about for like the HC8 and other kind of where you want to have microcontrollers talking on a single wire. This looks very reminiscent of I2C, right? Where we have an open drain or open collector setup. So we're going to have a pull up. So this is pulling the line to the idle state. And then anything that wants to talk will create a 0 bit by pulling the line to ground and then releasing it to the pull-up for a 1. And technically, I'm showing this kind of as this is the master and these are the slaves, but technically any device could talk to any other device in here. Now notice, since they're all connected together, just like with I2C, somewhere in your protocol, you would have to have an address scheme so that if this guy wanted to talk to this guy, for example, it would have to, this and this, they'd have to agree on some mechanism in the packet that says, hey, this is for you, because these guys would hear that message. They just have to ignore it because it was not for them. So oftentimes in the simple stuff that I do, I will have a message address where 0 is considered a global message, so everybody responds to it. And then 1 and higher is an individual device address. And back in the golf course industry, when we were doing networked kind of control systems, we also had group addresses. So we could say, okay, everybody on the back 9 shut down, or everybody on the front 9 shut down. We had group addressing that way. So again, that has nothing really to do with serial data or the mechanism. This is the protocol, which is how we're sending information over the, our serial scheme. Any questions? Okay, good. This is going to be easy.
John, when you're ready for intermission, let me know.
Well, I just needed to take a sip. I was starting to get dry. Okay. RS-45 is a two-wire communication system, but it's not transmit and receive. It is like a one-wire in that you're transmitting and receiving on the same pair. It's a pair of wires that use a differential voltage situation, so that having this differential transmitter receivers on each device, and then what we do is we twist the wire together so it lays closely together. The thought behind that is if we get some kind of electrical interference that impacts one wire, it will impact the other wire equally because they're laid on top of each other and twisted. That way the levels, let's say we had a voltage that wanted to push it up, well, they would both go up so that the difference between the two outputs would remain steady. And in this case, this is how, you know, a DMX situation is configured. So if you've ever been to the theater, or, you know, I'm going to pick on Francis again today. I'm sure, you know, he's on Friday nights, he's out at the discos having a great time with all the crazy lights and bumping and grinding music and all of that. Yeah, there you go. See, you know, the DMX is a one-way protocol over RS-45. And it's fun and it's simple, and it still gets a lot of use. Now, DMX is kind of interesting because it's not just serial data. What DMX does, and I probably should have made a diagram, but it actually puts what's called a break onto the line. So before it sends all of the packets to the fixtures, it pulls the line to a low state and it holds it there for, I think the spec is 92 microseconds minimum. It's about 4 byte periods. And then it releases it for a couple of bit periods. That transaction, that break plus what's called the mark after break, that is intended to tell the receivers, we're starting a new transmission, reset your internal byte counter. Because in what we call a full universe in DMX, after the mark after break, we will transmit 513 bytes. You'll often hear DMX, I generally call it just DMX, but you'll see it called DMX 512. There's actually 513 bytes transmitted because the first byte, the 0 byte of the packet, is called the start byte. In DMX, that's always 0. There is another variation of DMX called RDM that I've looked at a little bit. I've never actually worked with, but it uses the same hardware, but RDM uses a different start byte. The idea is that modern fixtures that see a non-zero start byte should just ignore the packet because it's probably an RDM message to one of those fixtures, and then that fixture can send a message back to the controller. This is important because, for example, in lighting, you know, as lighting fixtures age, their color changes, and this can be problematic. And so fixtures, for example, will keep track of how long they've been operating or what their temperature is. So you need a bidirectional thing in that. So in DMX, it's just one way. In RDM, it can go too, but it's running on the same hardware. And the nice thing is, again, it's like this. This looks very much like the I2C stuff, right? It's multi-dropped. And we can go back and forth. So we can talk to everybody or we can talk to individual stuff. And here is a fun project that I did using DMX and the Propeller. Now, it was a Propeller 1, but it's a Propeller nonetheless. My friend Matt Hawkins is an amazingly smart guy and a creative guy. So by day, he's a high-end IT guy for Microsoft, doing work with the military and other crazy customers. And at night, he's an amazing sculptor and painter and monster maker and TV writer, and he's very, very creative. And about 3 or 4 years ago, his daughter, so it was at the height of the popularity of Stranger Things, you know, said, hey, can we decorate the house like Stranger Things? And Matt went all out. So he did a screen capture from the show and he made a duplicate of. So those of you that have seen the show know what's going on here. There's a, for those that haven't, the story involves a little boy that gets trapped in an alternate universe kind of thing, and he's able to control light bulbs. So his mom sets up a bunch of Christmas lights on the wall and paints letters there, and he can send messages to his mom through the light bulbs. Matt wanted to duplicate that. Well, we found a company called Holiday Coro that makes WS2811 Christmas lights. These are the same lights that we were using 6 weeks ago, except these happen to be full-on C9 Christmas light style bulbs. And so Matt, who has done a lot of show control for very high-end companies, he has big show control software. And he said, hey, can you help me make a module for this? So what we did is we took, again, the HC8, which is a Propeller 1 board that has RS45 on it. And we did something that is a very common thing at Disneyland. I've worked with them many times on DMX projects. We made a custom DMX receiver that was smart. And the idea is there were two channels we were paying attention to. One was kind of a what macro or what method inside our code to run channel. The other was a trigger channel. And so what Matt would do is during the course of the show, his big show control software at a given point would set the macro that he wanted to run, which would spell out a specific word. You know, we would go through and we'd know, for example, if we wanted to spell help, you can see the lights are normally lit. So we would dim and then relight the H, and then dim and relight the E, and then the L, and then the P, so you could spell out words. And so I wrote the code to do that, and then I would say to him, okay, here, you can kind of use this as a template. You can see where the letters are, because we had to go, you'll notice that you know, it's not a one-for-one relationship. We had to know which address in the string corresponded to which letter. So we created a table inside the software that was really easy to do, and then we could spell anything. And then his show control software would set whatever thing he wanted to call, and then here was the key. Then the trigger channel, you know, a few milliseconds later would be set to the trigger level. The controller would see that trigger level go to, you know, high level, and it would then grab the control value and say, okay, this is what I'm going to do, and then do that. This was taught to me by my friend Rory at Disneyland, because he works in their special effects department. And in fact, this board was designed based on his requirements. In fact, the original prototypes of this board are still running in the Haunted Mansion down the way at Disneyland. And, you know, they needed DMX capability, but they needed, so for example, this has an old school 9-pin DMX switch on it for the address. And then it has the RS45 circuitry. And then, of course, it's a completely programmable propeller. We can do anything we want with it. But in the case with Disneyland, there's, you know, it's a big corporation and lots of squabbling between groups. And the lighting guys tend to have control of things there, and they would want to control the props. And Rory say, yeah, no, you're not going to control my, you know, $100,000 animatronic. Just tell me when you want me to do my thing by setting a DMX channel to a high level, and tell me what channel it is. So I built a DMX receiver cog for this. I also used this in Matt's project. So when the DMX stream was coming in, we could just look at a specific channel and see it change to the trigger level and then do whatever we wanted. So you know, I have, for the propeller, I've done DMX output and DMX input. They're both pretty easy to do. I didn't put it in this presentation because I think I've shown it more than enough times. Those of you that have seen my other presentations, though, remember Annie and Tibbers, you know, the giant bear and the little girl. That's a giant DMX project. It has one Propeller 1 and then a whole bunch of little DMX bricks that are, you know, placed through the project. The propeller knows each of the sections on the display and does the animation. In fact, I have 5 animation cogs running simultaneously. Each of those animations feed their data directly into the DMX stream, which is running in its own cog, and it goes out. So we have the ability to do this very complex animation. And if we need, you know, I think I told this story, Steve Wang, the boss of that particular shop, you know, he's a Hollywood heavy, and he's very specific about what he wants. So he would say, hey, John, can you shut down that tree and that tree and that tree and just show me this tree? And we could, because each of those elements had their own animation cog. So I could shut them down. We could tweak, you know, we often did really finicky little timing things, but he was the boss. We gave him what he wanted, and then we could turn everything back on and see it all together, and away we went. It's really fun. So this is one of my great joys with the Propeller. I've done lots and lots of animation and lighting and stuff with a very simple serial protocol called DMX. It's still very viable. Anyway, just for sharing stories, this was such a huge hit. Instead of staying up just Halloween weekend, it stayed up for a month because people were coming from all around Southern California to see it. It got on social media. People come out, hey, can we see the Stranger Things thing? And I don't know if this is true. I'll have to ask Matt, but I heard a story that people from the show, production people from the show, went to his house to see what he had done. Because, you know, in their world, in the TV world, they're doing things with special effects. Matt did it, you know, with some electronics and some programming and hardware. But yeah, for those who, you know, for you young people, this is what phones used to look like. This thing over here hanging on the wall. See, Francis is laughing because we're probably around the same age. We've both had phones that hung on a wall that you had to pick up the receiver to answer the phone, and you didn't know who was calling when the phone rang. It was always a surprise who was calling. At any rate, this Matt, because his daughter, she's kind of come out of her shell now, but back then she was a little introverted, and she asked for this, so he really went all out, and it was fun. I had a great time helping him with it. But he found that phone, which matches, you know, what was in the show on eBay, and bought it. And the way it all worked out, you know, he'd have a number of guests come into the house. And it was not just for reference too. It was not just the living room. Over here off to this side was his dining room. There was a bunch of lights in there. And then if you drew a line from one end of the couch to the other and extended it, that would go down a hall. And at the end of the hall, he built a flexible wall. Those who've seen the first series of Stranger Things know how the end happens with the weird flexible wall and the monster. He made the monster suit, and it was a fog. In fact, we used another one of the HCH to control a fog machine and some lighting at the end. It was really, really extravagant and fun, and a huge, huge hit with the neighbors and, you know, people around Southern California. Okay. Just to show you that protocols are, you know, the only thing that changes here. This wiring diagram looks suspiciously like the DMX wiring diagram, except you'll see I have arrows going back. And MODBUS is another protocol that runs over RS-485 wiring. That's a very, very simple serial protocol. It's easily implemented on the Propeller. I've done on the Propeller 1. I'm rewriting a driver for the Propeller 2 because it's very popular in industrial environments. In fact, I think I shared, I don't have it handy. I know I shared in one of my other presentations a really big board that was the HVAC controller. We used MODBUS on that to talk to an HMI that was about 4,000 feet from the Propeller. So the Propeller had a little local LCD, and then there was a big fancy HMI in another building that was about 4,000 feet away, and that was all part of this MODBUS network. So very, very simple, fun protocol to deal with. Oh, okay. We're done with the presentation. We can look at some code. Can you see my editor?
Yep.
Okay.
John, since you're showing Prop Tool, I have an update from Jeff.
Oh, good.
My email to Jeff is, Jeff, where is the release of Propeller Tool with debug in it? And he says, oh, great progress. Fixed 2 showstopper bugs yesterday and today. Chip's working on another bug I found. I'll have this released Friday. Tying up loose ends now. I've been working since 3:30 a.m. except for about an hour and a half. All of Chip's debug examples I've run work the same in Propeller Tool as they do in Peanut now. Getting back to it now.
Excellent. Yeah, Francis apps too. Now you can get your quick byte, Francis. Okay, so this, again, these are going to be very simple. We're going to do as we have done before. I'm going to show you how we could do it in spin. As I said earlier, doing serial in spin is not terribly practical, although we can do it and we have done it. It's, you know, in the P1, we would sometimes do it if it was, we didn't need very fast serial. It's just a couple of bytes, and especially if we didn't need to receive, which is a little bit more problematic when you're doing it in spin, because it saved a cog. Remember, you know, we couldn't do buffered serial without a cog, and so anyway, if we look through here, you'll notice this is, you know, the standard program. Now I grabbed, this is kind of oriented towards PSD, although I did test this for the guys that are running Flex Prop. I did test this. It should work if you have a problem. I think we've been through Flex Prop enough in the changes between PSD. You should be able to sort that out, but I'm pretty sure it'll work. You just have to change to ANSI mode. All looks the same. You'll notice though we don't have a serial object. And so what we're going to do is we're going to create our own serial down here again for demonstration purposes. And you know, this is code that was adapted from P1 code that we've used many times. So you'll remember back from the presentation, we had to know the timing for each bit. And then we're going to do this, since we're going to use this to talk to our terminal, which is a 2-wire connection, we need those two. So what we're going to do is I've made this little start method for our embedded serial that drives the transmit pin high because that's the idle state for true mode. And then it floats the receive pin because we need that to be an input. And then I'm going to take this system frequency in clock freak and divide it by our baud rate, and that will give us this variable called bit ticks, which is the number of system ticks in 1 bit. So we'll pop down here because the transmit byte is the first thing that come to attention. There's a couple of things going on in this line. You'll remember we have the data byte. We also have a stop bit and a start bit usually. And so the stop bit is going to be, it's going to follow our data bit and it's going to be high. So the way that we're going to do that is we're going to OR hex 100 because this is where this is a space for our data to go. And remember, OR with 0 doesn't change anything. So this will put a 1 in the stop bit position initially. But now we also need to have a start bit. And so what we do is we shift everything left by 1 bit. That puts a 0 now in that LSB bit, which is what we want for a start bit, right? Remember, we want it to go low. And so now we have prepared a 10-bit value that we can transmit out. So and this is all timer based. So we grab the system clock. We're going to send 10 bits. So we'll wait a bit period, and then we're going to grab a bit and we're going to write it directly to the transmit line. Now, this works because even though this is, you know, a multi-bit value, this is only indicating 1 pin. So that means we're only going to write the LSB of it. We don't have to mask it out or do anything like that. It's not necessary. It'll just write the LSB. And now once we have put that out on the line, then we can get rid of the bit we just transmitted by shifting everything to the right by 1 bit. And so this will, one at a time, it'll go from the lowest bit to the highest bit, and it will insert this bit timing in between them. Now remember, the last thing that we did was leave the line high, so that will leave the line in the idle state. And to be honest with you, I often do this, you know, just in case I do something silly and think, oh, so here, pop quiz. If I change this to 11, am I going to have a problem? I need the Jeopardy quiz theme to be playing now.
That leave a 0 at the very end?
Yes, it will. I'll send 11 bits, but the last one will be 0, which will look like a start bit to the receiver and will create a problem. So sometimes you'll see in my code, I just arbitrarily I do this, because that way I can change this if I decide, you know what, I want an additional start bit and I don't have to worry. So I did the one here just to try to keep everything aligned. But in my practical code examples, you'll actually see this so that I can change the number of start bits without worrying what state I'm going to leave the transmit line in after the byte has been transmitted. So that's how we transmit a byte. Easy peasy, lemon squeezy, right? The receive is the other side of that with a little bit of extra work. Like, let me go back to my presentation. So you'll remember that we're going to look for the start bit, and then we don't have to sample anything for 1.5 bit periods. And so you can either wait 1.5 bit periods. What I actually do, and this I think becomes a little more practical, is after the start bit, I just wait for the middle of the start bit and then start doing the 1 bit periods. Either way works, and I've done it both ways. So we'll go back here. So we can see that. So this line is just going to sit and wait for the receive line to drop. Now remember, this is connected to another transmitter whose idle state should be 1. So the repeat while pin read RX1, it says, hey, as long as that's coming back as 1, stay right here. The other way I could have done it is, you know, repeat until pin read RX1 equals 0, you know, to indicate that's a start. 6 of one, half dozen the other. They both work. The idea is we're going to sit on this line of code. That's why there's that comment. This is blocking, so be careful with it. Something has to come in to get past this method. Anyway, once we get past that code on line 212, then we're going to initialize our timer, and then you notice we're going to add bit ticks shifted right by 1. So remember, if we shift a value to the right by 1, that's dividing by 2. So this becomes a half a bit period. And now what we do is we drop into our loop. Now remember, we only have 8 bits. So what we've done is we already added the start of the clock plus a half a bit to our target. And now the first thing we're going to do is add another bit. So this is where we get our 1.5 bit times before we sample the first bit. And now, you know, this is kind of the opposite way. We have to make room for the bits. These are also coming in LSB first. So we shift our result variable to the right by 1 bit. We read the pin, we sample the input pin, and then we stick that into bit 7, which is the MSB of our byte. Remember, that's going to chunk through, you know, with each right shift. So the first bit that comes in will land in bit 0 when we're done with the process. And this is probably more than is needed, but I always end up doing a little cleanup. We end it with FF just to make sure there's no shenanigans in the value and send it back. So this works. And like I said, now, you know, again, I'm very easily entertained. It made me laugh out loud. I kid you not. When this code, which is interpreted spin, would do 230K baud. Because on the P1, we could do, I think, the top end, and you had to be a little careful not to add any fluff to code, which I sometimes do. You could do 19.2K baud at 80 megahertz. So at 200 megahertz in the P2, you can easily do 230. And I'll probably test sometime to see how high that can go. Again, I've standardized on 200, but if I needed it higher, I could always crank up my clock frequency too. Again, It's there, not practical. I think if I was going to do this for quickie kind of things, I would probably just do transmit because, again, receiving blocks. And there are plenty of devices like serial LCDs or output expanders or other things that only need to be sent to. We don't need any data back. So this is, you know, okie dokie. Just a thing on sending data serially. If we want to transmit a string, we'll have methods that are usually called str in any kind of serial object. And this is to transmit, you know, a string of characters. Like a lot of other languages, Spin doesn't have a string type. So what it does is it treats an array of characters as a string, so long as we terminate that array, the last character, you know, the character that immediately precedes, that follows our string, that has to be 0. Because that's what this will do. Now, it's a little sneaky the way it's doing. Since we don't know how long the string is that gets sent over, we ask it. Now, internally, what string size does is it counts up the number of characters until it hits a 0. So that will tell us. If I send it over, you know, string parentheses, quote, JON, close quote, close parentheses, then even though embedded in the code is JON 0, this will amount to 3 because it doesn't count that 0. It's just the characters that precede it. And then it will transmit that. And, you know, we're transmitting the character at this address, and then we increment the address. So you'll see this. This is very common. It's why we do string stuff.
Johnny, wouldn't it be like if stir size recomputes the length of the string each call, wouldn't it be more efficient to call it once and then just loop a loop counter amount of times?
It does not. When you have a, because I'm treating this as a singular value, this expression, it gets evaluated at the start of the loop and it does not get reevaluated while the loop is running.
But you're advancing the pointer.
Right.
Oh, I see. It's repeat.
Doesn't reevaluate.
It doesn't.
The expression each loop.
Yeah.
Okay, I understand. I get it now. Thank you.
Okay. Yeah, there's an internal control variable that gets set to whatever this expression comes to. Now, if I had a while or an until, then that creates a reevaluation situation, but not this one.
Yeah, sorry, I misinterpreted repeat as like repeat while true as opposed to repeat and time.
Yeah, no, yeah, you know, this is, you know, again, this is repeat the number of characters that are in that string. And I have, in some of my code, you'll see I have also I often have routines called substring, where you would have an additional value that you would pass along. And what it will do is it will go either to that many characters that you specified. You know, for example, my given name is Jonathan. So Jonathan. If I said, you know, Jonathan, substring Jonathan, comma 3, it would just print out JON. But if I just sent over JO, it would stop because it will, that particular method does see if it hits a 0 early, it does an early exit. So you'll find that in the full duplex serial, and you know, and in this, these are very common things. I didn't create any of these things. I just did them my way. I know that I see Ray Roddick showed up on my screen, so he's doing a lot of work with serial stuff. He's probably got more features too. There are lots of creative ways to do that. But those are kind of, you know, sending a character and receiving a character and then sending a string. Those are kind of the core for me serial things that if you have those, you can do a lot of stuff. Now, everything built on top of that is kind of extra, you know, and not unnecessary extra. In fact, it's quite convenient. It makes our life nicer. But these are kind of at the core. So if I'll run this, so you don't have to, you know, it's a very simple thing where it's just doing a silly menu. And, you know, now I'm using the RX to get my character choice. And then in the menu, it has a situation where if I have a bad input, then it won't. You know, it deals with that. But again, super easy. And yet we do this kind of stuff all the time. In fact, in every presentation I think I've done since Christmas, and we've been doing this, I've had some kind of menu or configuration thing that uses these capabilities. So we'll just look, sorry, this always happens, the control bar for the Zoom meeting goes right on top of my screen, so I can't see things. So here's the second version of that, and I won't run it, but I'll just show you that one of the things I really like about the Propeller and the P1 and the P2, but the P2 in particular, is that the assembly is very close to the high level stuff. I mean, they're written by the same guy. And so, for example, here is the assembly version of transmit. So with this, because it's running at assembly speeds, I could run, but you'll see it's nearly 1-for-1. Here I'm adding in the stop bit. I'm shifting left to create the start bit. We grab the timer. Now this repeat loop is saying, for those of you who have not seen assembly in the P2, it says repeat the next 4 instructions 10 times. So that's 1 for each bit. And so I'm going to do a shift right. Now the order here is a little bit different. I'm going to do a shift right of my value, and I'm going to capture the LSB. Since I'm shifting to the right, I can capture the LSB in the C flag. And that's the bit that I want to transmit now. So there is this really convenient instruction called drive C, which just sets the output pin, in this case I'm calling it TXP, to whatever is in C, which is that bit we just captured. And now I've created this timer called bit count. I'm going to add in my ticks and set it into this version of the timer, and then wait for it to expire. Very, very simple. And I use this a lot. In fact, you'll see this is almost line for line from my DMX transmitter. The receive, again, a little bit more involved, because what happens in this case, we don't know when the start bit is going to come. So this is the way that I approach it. I arbitrarily grab the counter and stick it into the timer variable. And then I look at the receive pin and capture it in C. If it is high, so if C means if the C flag is 1, which would mean the line is high, then jump back and do that all over again. So it's going to sit here spinning, waiting for the flag, the RX pin to go low with the start bit. Once that happens, then we fall through. We've already started our timer, so now we can get set up. I'm going to grab the ticks. This is my bit ticks. You see, I've had to make a local copy here because we cannot use global variables or global constants in inline assembly.
Hey, John.
Yeah.
Just a thought. If you put the get count after the test loop, then the test loop will be tighter because it will be able to register in 2 clocks less. And then you'll be able to still get a pretty fresh copy of, it'll only be up to, well, 4 plus a loop clock. So I don't think it'll be any more stale, but it'll get your timing tighter.
Okay. So yeah. All right. So just move, you're saying move this line to here.
Right. Yeah.
Okay. All right. Easy peasy. Again, with the baud rates we're running, a couple of clock cycles won't hurt us, but I understand what you're saying. This is doing that half bit thing. So we grab, this is our bits in a tick. We shift it right by 1 to get half, add that into the timer and wait. Oh, in this case, what I'm doing is, oh no, yeah, this is waiting now here. This is waiting for the middle of the first bit that I want to sample. And now in this particular case, we have 5 lines to do, and we're going to do that for 8 bits. And then we will, same thing. We wait for the timer to expire, sample the line, make room in our bit, and then stick it in. Very, very simple. And so with this, of course, in assembly, you can get much higher baud rates. If you look in a lot of P1 programs, mine included, and I think I borrowed this from my friend Peter Jakacki, we can't actually unroll the code. So you just do things, you know, in a whole bunch of instructions. And, you know, that's how in the P1, people were getting 2 or 3, you know, megabits in or out by unrolling the code. So for the debugging things. In the Propeller, like I said, it's so crazily fast that that doesn't seem necessary. Again, I use assembly in a couple of my drivers. For the most part, though, we're going to use, I really want to just move this.
Before you go on, John.
Yes, go ahead.
Before you go on, can I
Yeah.
make a suggestion? I don't know whether it's capable in embedded assembler, but Chip can probably answer me. But with the rep instruction, the #5, we've normally been using an @ sign with a .rep as a label and putting that label on a line below the bit.
Yeah, down here, yeah.
Yeah, and it saves having to count. And if you slot one in, you don't stuff it up.
You're right, Ray, and I do that if it's more than a few lines. Yeah. So what Ray is saying is that I could say I could do this.
Yeah, I agree. For just a couple of instructions, I tend to just put the number because it's, but the only gotcha is if you have a pound for a big
Yes.
constant, that can really hose you up.
Yes.
You need no, that's right. That's right.
Yes. So yes. So you know, again, it's a stylistic thing, but I absolutely agree with you, right? Because I have some longer sections of code where I don't want to be bothered, or if I have if I have, as Chip was saying, if you have a pound where there's going to be another instruction inserted, I don't want to take a chance, and so I just do the label thing. So you know, again, the nice thing is the flexibility of the Propeller to let us write code that works really nicely. So.
John,
Go ahead.
another question for you too. I got to be reading this wrong. It looks like you're waiting 2.5 bit times. Aren't you doing the 1.5 wait and then waiting again before you sample?
No, because I count.
Oh, he's reading, okay. He's reading a 1/2 bit time there.
Oh, okay.
And then he does a whole bit before he grabs the first bit.
Gotcha.
Yeah.
Yeah, I was
Yeah, because I was thinking,
half.
see, you almost talked me into that, Stephen. I was saying, wait a minute, I tested this code. I'm getting the correct values in.
He's a hypnotist.
Yeah. It's like I tend to believe my friends. You know, my friends are smart people. So if you say something, I'm going to believe it.
That's why I said I got to be getting it wrong, because I figured you would have tested it.
Hey, John, right. There's one other thing. Just it's trivial, but you see how you're doing the wait counts?
Yep.
You can set up an event to trigger on a negative or positive edge of that RXP pin, and you would do it as you came in, and all you'd have to do is, like if you said set SC1, and then you took that pin number and then ORed it with like 0, 0, 1, or no, 0, 1, 0, because you want to go 1, 0 is a negative transition. So if you took 1, 0, shifted it left 6, and ORed it with that RXP, and did a set SC1, what you could do then is a wait SC1, and it will actually wait for the it'll wait for the event of that SC1, which is pin RXP going low, and then you'll be like absolutely on the clock edge without any kind of jitter.
Okay, well, that's something to explore.
We do that. Talk about that in the future.
Yeah, let's, because I have not done anything with events yet. This is kind of, you know, this is really an adaptation of my spin 1 code that I've been using for eons and eons. And again, the nice thing, I mean, you know, with what you've given us, it's immensely flexible. So we have lots of different approaches that will all work. And again, here in this case, we're doing low baud rates. But you know, the events thing, in fact, I was talking to my friend Matt last night, the guy I mentioned earlier, did the Stranger Things house, and he said, hey, wait, does the Propeller 2 have real interrupts? I said, yes, it has real interrupts. And And he said, I always liked that we never needed them. I said, well, you don't have to use them. They're just there. So there's plenty of that to go around to teaching stuff. But anyway, let's look at one last thing, because it's the one we're going to use most of the time. Again, this silly bar is in the way. And this is the Smartpins version. And so what I'm going to do is I'm going to click over on the full duplex serial object that we've been using for ages and ages, and look at that. So in this particular case, and I'm going to ask you to chime in a couple of times here, Chip, we are going to use the smart pin. So the transmit pin, if we're using it, is going to be set up as an asynchronous transmitter for 8 bits at whatever baud rate we are telling the system we want to run. And then the receive pin is going to be set up as an asynchronous receiver. So there's 2 smart pin modes because we have 2 pins. So that's why I was saying that while you could, if you wanted to do a bunch of monkey motion and reconfigure the pin on the fly, for smart pin modes, I just want to do that as full duplex. I don't want to reconfigure smart pins on the fly, although it's possible, you could do it. So this, and I tried to make this as close to the P1 full duplex serial as we could. That was originally written by Chip. So you'll notice that not all of the modes that we have in the P1 are available. For example, we don't have the open baud modes in the oh yes we do. There was something that was missing. Oh, we don't have half duplex. We can't transmit and receive on the same pin, which we can do in full duplex serial on the P1 if we use the same pin. But what we're going to do is, so here, for example, well, we'll talk about this. And I was going to ask you to chime in here, Chip, because I forgot your explanation, but we're going to take our baud rate and we're going to run it through this equation, which was suggested in the documentation for our bit timing. I think the idea behind this is it puts the bits for the baud rate in the correct place in the value, and because of this it does a little bit of rounding up and clean up properly. Did I miss that?
Yeah, what that does is there's only like so many bits. So we're capturing, let's see, 22 bits of baud data, but I only have like, I think 16 bits of counters, like flip-flops available for counter. So if the top 6 bits of that big number are 0, then it uses it like shifted left, and then so it's using the same number of counter bits because we only have so many flip-flops in a smart pin. But for lower baud rates, it allows you to express what wind up being fractional bits with fractional bit times, so that you maintain precision.
Okay.
So sometimes it might do like 5 clocks between bits. Sometimes it might do 6 clocks between bits.
Got it. But it averages out the baud rate.
Yeah, it averages out to what you need.
And then, you know, and in the case of many P2 things, we actually want 8 bits, but the value we're going to put in is that -1. So from a code style-wise, I see Chip do this a lot, and I've tended to do that just to remind me, hey, this is 8 bits. I could have put a 7 in there, but then if I say set 8 bits, it becomes, you know, when we're writing code, I would suggest when we're writing code for others, we don't want, you know, head scratching moments for people saying, well, it says 8 bits there, but it's 7 there. What's the story? So this kind of helps with that. But anyway, the low nibble, I guess, of the baud configuration is the number of bits. And remember, we're typically doing 8, but we could do the Coke machine thing and put a 9 in there and do a 9-bit data word. So here's the configuration for the receive pin. Again, like in the original version, if we're not using the pin, we pass -1 as a value. So we're assuming we will. So we're going to use the async mode. And then if we have the invert, we will add that flag in, and then we'll do the pin start. Remember, when we're using pin start with a smart pin, it clears out everything that was already there. So you don't have to worry about previous configurations if you're doing this in the middle of a program. Pin start resets everything in the pin, and then sets up this mode. So we're setting our RX pin to our asynchronous mode, and it could be inverted and at this baud rate. And I don't remember why we have a Y0, but it'll come to me in a second. And the same thing now with the transmit pin, there's a little bit more going on. It's a transmit pin, so we need to control the output, so we have to enable the output. Remember, Smartpins are using the direction bit of the pin as an on and off control. So if we actually have to do output from the smart pin, we need to set that. And then, you know, same thing here. It's an inverted output. This is an open output, so that we can, you know, if we had a pull up on the line where we're talking to another device, we can do that. Same thing here, where we're doing an inverted mode, but, and then we're floating the output low and just driving it high.
Hey, John, the reason Y is 0 is because it's unused. I just looked it up.
Okay. I thought that was the case because this is the receive side. We're not sending anything. So here we're, you know, we're setting up the receive pin and ready to go. And now here's what's going on with this particular object. What I did is the hard part, the UART parts in the smart pins, there is a background cog though. And what it does is just watches for a transmit value from us. If we say, hey, transmit something, what the background is doing is looking at our transmit buffer and saying, hey, is there anything in it? If there is, put it into the smart pin and let it go out. And then it says, oh, hey, is there did I receive anything in the RX pin? And if it did, it grabs it out of the RX pin and sticks it into our receive buffer. So there is a cog used in this driver, just like in the P1. In the P1, though, there was a lot of work going on because, you know, if you look at full duplex serial in the P1, it will make your head go a little fuzzy for a bit because it's doing what Chip calls ping pong multitasking, where it's divided up the transmission and the reception into small chunks of code, and then it's, you know, bipping back and forth between them. It's quite complex. And then it is also doing the buffer management. Here we have it easy, and I had concocted this hoping that it would make multi-port serial easy-ish. I don't know. Now I know Ray has been working really hard and seems to have a gajillion serial ports running simultaneously. So hopefully this configuration was useful. He's probably too polite to tell me it was rubbish if it was. So anyway,
I certainly used it, John.
If we look down in the, if we go down to the assembly portion, again, this is really fairly straightforward stuff. So here, and you notice I'm calling it UART manager. They're not UARTs, they're where the pins are the UARTs, so this is just managing them. So what I do is the first thing, since the configuration passes the pin numbers along, this little chunk here looks to see if the pin is negative, a negative value. It's looking at the sign bit in the pin. If it is, then it ignores it. If not, then it will come down to the RX serial and it will use the test pin of the receive to determine if there's a byte waiting in the pin. If not, we go back. If there is, then we use read pin to grab that. Now that's aligned up in the top of the data that comes back, so we have to shift it right by 24 bits. Excuse me, that'll align the LSBs. And then we're going to put it into the buffer. I won't bore everybody with this. It's pretty straightforward stuff. This knows where the buffers are. This is looking at the head, and we sort out putting it where it needs to go. So there's actually, it's a tiny bit of code to get that stuff in, so it can go quite quickly. The same thing with the transmit pin. In this case, if we're looking now, in this case, though, we're looking to see if the transmit pin is busy, because we might have just given it a byte and it takes a bit of time to go out. So this will tell us if the transmit pin is available. When it is, we drop through and we grab the head and tail pointers to see if there's anything that we need to send. If there is, we can grab it out, and then we use the Y value to put that into the transmit pin, and it gets sent out, again, without any thought from our part after that. So pretty straightforward. It's one of those things, it's a bit of a black box. You don't need to worry about it too much. Again, you know, Ray and Bob have been working on multi-port serial stuff. I have an idea for one I need for the laser tag, so I'm going to do my own version just as an experiment. But the great thing about the smart pins is that, you know, in the early days of the Propeller, people used to say, oh, it doesn't have UARTs. And we would say, oh, we don't care. We have cogs. We can synthesize UARTs. But sadly, a lot of people would not, I don't know, they just didn't get too excited about writing UART code. They didn't have to, but, you know, some of us liked it. Anyway, the great thing about the smart pins is now we have hardware UARTs, so we can do crazy fun things with them. And then all the rest of, you know, full duplex serial, which I won't go through, is just fancy mechanisms to get data to a screen or to something else. So there's lots and lots of little routines. I did my best to kind of, you know, do formatted strings here. There was a discussion chip where it would be really nice if we had, I guess this is what polymorphism is, and maybe Roy will correct me. You know, it would be nice if I didn't have to have 6 versions of F string for the number of arguments that I'm going to pass over. It would be cool if the compiler said, oh, you're doing F string with 5 arguments. This is how you deal with it.
Yeah, we need that deal where we have default values, and it has to, it really act, I was thinking about it, it can't just be a compile time thing. It has to be a runtime thing because of the existence of function pointers.
Okay.
You just don't know what's going to happen. But it really wouldn't be much to add to the interpreter.
Anyway,
I want to do that at some point.
This is a workable thing for me. I haven't had any problems with it. I like, you know, since I do a little bit of Python programming and a little bit of C programming, I like having the printf, you know, stuff, doing formatted strings, and it just makes doing nice output very, very simple.
Yeah, variable arguments are nice.
Yeah. Yeah, I do. I would rather have that than default values. If I had to choose.
Yeah, same here.
Okay, so here is custom serial that, you know, since we talked about this, as I talked earlier about DMX. And so this is the DMX transmitter. Here's a very typical DMX circuit. And now what I did is that normally, under normal circumstances, a DMX universe will transmit 300, pardon me, 300. It'll transmit 513 bytes. Now, the DMX specification is at 250 kbaud. So it's roughly 23-ish milliseconds to transmit a whole universe. I also was telling you earlier that the way that DMX works, right before we send the start byte and then all of the frame bytes or the packet bytes, we send out this break period, this 92 microsecond, there's a constant in there, period that tells the fixtures to reset themselves. What I've found is that every fixture that I've dealt with, and I've written it into my own receiver code, will tolerate that break coming at any time. And so what that means, when I'm doing animation stuff like on Annie and Tibbers, I don't send 512 bytes. In the case with Annie and Tibbers, I'm only using about 40 channels, I think. So I have a smaller universe, which means my time from break to break can be shorter, which means I can get nicer, smoother animations. You know, again, the DMX standard is you're sending out 513 bytes. So if you're going to experiment with DMX, which is fun, and you can get DMX, it's plugged in here, so I don't know if it'll show. I can't reach it with the cord. I have a DMX fixture sitting here that I'm going to turn on. You have to check it to make sure it will tolerate a shorter than standard universe, because the spec says 513. But again, every cheap DMX brick that we've used in these movie props and these other display things, they've always tolerated short universes. And my own custom code for the that I use on the P1 and now on the P2, it can detect a break that comes at an unexpected time, and it's all right, we're going to restart everything, and it does. So in this case, this is well, this is P2 code, and I actually have this hooked up. I have a DMX board connected to my my Propeller, but here you can see that code that we were talking about. So here's the DMX process. Is that we drive the transmit line low and wait for the break timing. That creates the break period. We take it back high and then wait for that. The idle period right after the break is called the mark after break, or MAB. And so we wait. And then this is the hub address of my DMX data values. And then this is the number of slots I have. And so I make copies of those variables. These are going to get manipulated during the loop. And, you know, away we go. So we read a byte. Here's that start bit thing. Here's that thing I was telling you about where I generally use F instead of 1 so I can manipulate things. Add the start bit, start the timer. Here, this loop is very tight and tiny, so I'm going to run these 4 lines 11 times. So that's 1 start bit, 8 data bits, 2 stop bits, and that generates my DMX byte. I increment the buffer pointer and decrement the counter, and away we go. So I'm doing 2 kind of active timers in here because at the beginning here, I grab the counter and put it into this thing called break to break timer. And after the packet has been sent out through the DMX universe, and this all falls through, then we let the break to break timer expire, and then we start the process all over. Very, very simple and easy. And this code I have used in so many projects with Disneyland and movie business. DMX is a really old standard, but it's very simple and easy, kind of one-way control protocol, and you can do lighting stuff with it as well. It's lots of fun. So I have this old fixture from a company called Chauvet that makes inexpensive lighting devices. And so if I run this, so I don't know if it's showing up. It should see color on my face because I've got the light down on the floor. But so I have this fixture doing kinds of things. That's coming out of the I don't know if it'll show this. I have an eval board with a click module with an RS-45 click plugged into it. And that's what's sending the codes. Because remember, DMX is just a simple serial protocol that runs on RS-45 hardware. If I had a fancy HMI that used MODBUS, I could use this same hardware. I would just use a different software module because I'd have bidirectional and stuff going on. So really straightforward. The last thing I was going to tell you about now, I from a sports standpoint, IndyCar and Formula One is really what I like. I'm not a big stick and ball sports guy, but there was a Super Bowl this past weekend. And so for those of you that watched Tom Brady trounce that other team, you might have seen some aerial camera footage, and that was propeller controlled, believe it or not. There was my friend John Huffman of Johnny Jib. He makes controls and for a company called FlyCam, and they did some of the aerial coverage for the Super Bowl. So those were P1s. We haven't modified it to go to P2, but you know, we're doing, in that case, we're doing transmission of packets, and I thought this would be worth talking about in that, you know, the stuff that I've just done, it's all simple 1 byte things, but what happens if we have a situation where, and let me, oh, I closed John's program. Let me reopen John's program. So this is, you know, from my friend's program, and we have packets that we're sending. So for example, here is, and this is a P1 program, but this still applies to P2. Here is the packet that we send from the joystick controller out to the motor controller. And so there's a header byte that we know that this is the address. Now in this particular system, we only have 1 slave, but we decided to make that addressable in case we want to stack on multiple slaves. And in this case, it's pretty easy. We just have a command, and then we have a speed value. Now this is a signed word. And what we do on the other end is we turn it into a signed long. And then we have a CRC that is used with the packet to help us to make sure that on the other end, we got what we expected to get. On the receive side of it, now this is the master controller software. So this is what it's getting from the other side. Again, we have the header. 1 means, you know, the address is the base. Here is the current state. Here are limits bits. In this particular project is a target controller, so it's moving a target on a shooting range. And we have 4 limits. We have soft limits that the user can program in. We also have hard limits. There are these metal clamps that go onto the rope that John has these really sensitive inductive sensors that will provide a signal into, excuse me, I'm gonna turn this DMX off, that will know if we've gone past the soft limit, so we don't actually crash into something. So there's actually 4 limits. We have 2 soft limits, 2 hard limits. This is the motor speed. The particular motor speed controller that we're using uses a signed byte. Or it's a direction plus speed. So it's 0 to 255 for speed plus direction. So we just send it as 2 bytes. So this is the motor speed. This is the encoder speed. Because this is a P1, I wrote an encoder object that will give us position and velocity from the encoder object. And then these are position values. This is our current position. This is the A limit position, and this is the B limit position. And then we have a CRC for the packet. Now you'll notice that I've stuck everything as bytes here because again, this is a P1 project. I could do this a little differently with the P2, but that is worth showing because you may run into this with other types of devices. But for those who've not embraced bytemove, this is a place where it's really, really useful because you see here, these 4 bytes are going to be my B limit value, but I want to treat that as a singular long. So I can use bytemove with this address to move those 4 bytes into a singular long. And we'll have to do this sometimes with data packets. You know, we made decisions on how big the values were. We wanted to keep things as small as we could, so we're not sending a whole bunch of bytes we don't need. And but then still, once you have them, you've got to put them into something usable in Spin. I also ran into, 20 minutes before all this started and I wanted everything posted, I tried a little demo program that I wrote in FlexProp, and FlexProp, unlike Spin 2, reorders variables. It's a common thing compilers do. One of the things that happens though in Spin 2 is that the variables are laid into memory in the order you define them. It's not based on size anymore. And this can be a very useful feature. It's kind of like, in C, there's this struct type that does that, but that's kind of a manual override of the normal placement of values. And what I found out the hard way, I think Dennis pointed this out with my initial version of my little wave player, is that FlexProp will reorder things when I wasn't expecting it. So doing it this way is a little bit of extra work, but it allows you to lay things in where you need them. So I have a really simple little demo. That's program number 3. That's kind of, it's a really a gross simplification of, you know, my friend John's program. So here's my packet. I have an ID, and then I have a sequence number, and then I have this random value. So I have a byte, a word, and a long that I would normally like to deal with, just as I've done here. And so what can do, and this is, again, you'll see I have a lot of 1 and 2 line methods here, but this is what I did when I was creating John's program. I said, okay, let's have a method that just makes the packet so that we can put it together, because then we can look at it and debug and see we're getting the right bytes in the right places. That's what this does. It shows us where they are, and then this sends the packet out. Now, in this particular case, what I've done, you'll notice, again, this is really simplistic. I've got 2 objects for serial. One so that we can see stuff on the terminal, and this comms one is my little test thing. So what I've done on my propeller board is I've just wired my transmit and receive pins to each other with a jumper. And I'm going to transmit from the comms TX is going to loop right back into the comms RX. And if we run this, so what happens is we're going to transmit that packet. Now, this wait is completely unnecessary. It's for dramatic effect, because within a byte period of the transmit finishing, the receive will be finishing as well. And so then we go get that packet. Now, that's where it's a little more interesting here. Well, I'll go through the whole things. Here in the transmit, I'm taking these bytes, and because I want to change them. I want to treat these data things as if they were regular variables. I can't, because I've broken them up into bytes. So what I do is I have a work variable that I'm going to clear here. I'm going to use bytemove to take the 2 bytes that are at sequence and stuff them into this variable. I'm going to add 5 to that, and then I'm going to put it back. So it's a little bit of work, but it serves a purpose where now I have things laid into memory. And this is just a random value. So I create a random value, and then I stuff it into that section there. I didn't put a CRC or anything on this. And then this, in this case with the show packet, since I want to use my formatted strings, I would like to have them reconstituted as full bytes. So here's bytemove the other way, where I'm taking the 2 bytes that are at sequence and I'm stuffing them into here, and the 4 bytes that are at this location and stuffing them into here. Now, here's the thing with the P2, and if this is something I did not test in FlexProp, but I do know in Propeller, because there's no forced alignment anymore, I could, the sequence is a word and random value is a long. I could have used word move here and long move here and add 1 and 1, and that would work. But I don't know if that'll work in FlexProp. Since I now have these in standard variables, I can put them on the screen. To send that now, since this is just a big blob of bytes, well, a small blob of bytes, I can point to it and then just transmit them out, and away they go. On the receive side, it's the same thing. Since it's such a small blob, I just created a local byte buffer. Excuse me, for those that haven't used that, you can have byte and word local variables. You just have to explicitly declare it before each variable. So here is the receipt. Now in this case, I'm using RX time. So if something breaks, the receive will time out, and I'll end up just getting a -1 in, which will turn into an FF in the byte buffer. And then I'm going to move the 2 bytes in the buffer to this variable and 4 bytes in the buffer to that variable. These are globals. Here, this is a 1 byte thing, so there's no real work to do there. And then I can display that. So again, really, really simple, but I'm a really, really simple person, and I will often do these kinds of things just to test ideas. So there's a bunch of you that are far more advanced than me, but for the new people, I would suggest don't be afraid to do really simple things like this to prove concepts. And so, you know, this is nothing terribly exciting. You can see this is what's going out. And if we look, you know, we get the same thing back in. This is just going through a little tiny wire. But once I had this kind of idea working between the 2 boxes in John's system, then we said, okay, we have messages going back and forth. In that particular case, we actually had a command message that went out and then a response message that came back. So we had transmit and receive in 1 30 millisecond frame. And I ran into an interesting thing. In fact, I called Chip and talked to him about it. I talked to everybody I knew because I was really struggling because my frame kept breaking. And what it turned out to be that I discovered with my $12 logic analyzer is that in this code, there is a method here called CRC8 sorry, this is the newer version. So I had a CRC8 calculation in Spin that has been around forever. It's the same one that comes from the one-wire code, and the version that I use was written by Micah Dowdy. It works really nicely and it's clean and easy. And it's one of those things where it was a trap because it was cute little tiny bit of code that looked innocuous, but if you think about it with CRC, you end up having to go byte by byte, bit by bit. And in the receive packet, it's a few bytes, and it was taking an enormously long time to do the CRC relative to the size of my packet window, and that was breaking it. So you'll see now, this was the fix. Once I figured out that was the problem, then what I did was I just made an assembly version of that. So it went from, I think, 7.5 milliseconds to calculate a CRC down to 30 microseconds, and suddenly I didn't have any more broken timing problems, and we got everything working nicely, and it's off to the customer now. So the point of all this, and there's a couple of other things, again, for the newcomers, I see in the forums, people will say, hey, I want to send this hex byte. Remember, the system doesn't care. Hex is a thing for us. So if, for example, we say to the terminal, if we put into like term.tx, if we put term.tx parentheses 65, it's going to put an capital A on the terminal because 65 is the ASCII code for the letter A. Now we could put A in quotes. So that's a representation, because I see sometimes people they're wanting to send a single byte, but they're actually sending a string representation of it. So you have to be aware of that. And then if you're sending multi-byte variables, like I did in this little example and showing with my friend's program, the thing that I do, I don't know if it's considered a standard, but it just makes it easier to work within the realm of the propeller, is that the bytes in my packet, if it's a multi-byte value, go little endian, because that's how the propeller creates its variables. If you have a word, the low byte comes first, then the high byte in memory. Same thing with a long, it's the lowest byte, the next lowest, and finally the highest byte, stored in memory in that order. By doing that in your packets, then it just makes using bytemove very easy to put things in and out. So that's all I had for today. Hopefully that was mildly entertaining at some point. Steven smiled, so I guess it was okay.
Seems like it's a good lead-in for the XP work too.
Yeah, we will piggyback for sure.
Anybody have any questions for John?
So
I have a
John,
clip. I have a clip of that video, 15 seconds, if anybody wants to see it.
Oh, there's John. There's my friend I've been talking. I spoke with him this morning. I asked his permission if I could show some of his code, and he said, "Yeah, sure." So yeah, if you have that, John, that would be all right. Do I have to stop sharing, Ken?
You do.
Okay. How do I do that? Stop share. Okay. All right, John.
So now I have to share my screen.
You can share your screen. Yeah. This everybody. This is my good friend John Huffman.
Share.
Yeah, by the way, Ken, John called me this morning and he's sending me a fancy 24-volt stepper and a driver to play with.
Oh, good.
I said, oh, that's timely. We're going to be talking about steppers shortly.
You guys see the orange cone?
We
Yes.
Okay.
You're probably getting delays because, oh, is that their FlyCam that's going through? Cool.
Yeah, so that's running two P1s, one to drive it, and then one to pan, tilt, roll, zoom, and focus the camera. So it's got two subsystems in there, basically. It's all wireless, running over serial modems, and it works flawlessly. It's got all the safety features built in, two safety cables and one drive cable. It's got a DC motor with a, basically it's a direct drive DC motor with a pulley on it and a couple of antennas, and they operate it from somewhere in the stands or somewhere, wherever the facility gives them. They go to the Rose Bowl every year, to ESPN Game Day. So they're at all the big sporting events and golf. They do a lot of golf. They like this system because it's it doesn't require systems on the ground other than tethering the ropes, where their legacy system had a huge reel that had to sit on the ground and they had to rig it, and it had a huge motor. So this, they just basically string the ropes, they hang it, they throw the batteries on there, and they're ready to fly. So their setup time is a fraction of what it used to be. So they're very nimble, they're very happy. John did a great job on getting me out of the weeds on a bunch of the so they're a happy customer.
They're always exciting projects with John. In fact, now, so I'm gonna tell a story on you, John. You know, the last couple of conversations I've had with him, I keep saying, man, wait till you see the P2. Because if you look at the, you know, all the stuff that we've put together, like for this, when John, he just very casually said, oh, it does lens control. Well, the lens controls on a high-end TV camera have these very specific voltage ranges that you have to do things with. So with the P1, you know, we have a bit of electronics on the outside of the P1 to deal with all of that. And the DACs on the P2 will simplify our lives greatly with projects like this. The other thing, well, for example, on the, I was talking about with this other generation of FlyCam that we're doing, I had to write a specialty encoder cog for the P1 so that we would have position and velocity. Well, as you guys know from my presentation, you know, a month or so ago, the encoder object, Smartpins, so there's two versions of it. There is position and velocity. So we get as many position and velocity encoders as we want. I mean, we can accommodate with physical pins with no cog requirements. So it's really, really fantastic. So I'm looking forward to the opportunity of working with John on future, you know, control systems because he has interesting specialty clients, as you saw. I mean, we're flying the camera across a sports stadium, and you know, that's an interesting application. And yeah, I think we've been working together about 10 years now.
John, that's such an impressive project. I would love to share that with our customers if you're open to that.
Let me talk to my client and make sure that that's okay. He's a little weird about, as long as we don't get too particular in how he does it, because he likes to keep all that under his hat.
Oh yeah, I understand. It's
As
so,
you can see from the video, I mean, you can't really tell how we're doing it. You can just see that we're doing it, but I think he'll be up for that.
all of the really impressive propeller applications are ones we can't share publicly.
Now that thing moves, it can move up and down the wires, but does it have a system where the wires can traverse across the perimeter of the stadium?
That's the game cable cam. This one is mainly, they call it the fluff cam, where they're, I guess they could follow the game with it too, but there's a different system that's actually hard mounted in the stadiums.
Yeah.
Four reels, and the camera hangs on a pendant, and each of those reels works in concert with the other reels to raise, lower, move the camera in the XY axis. And
it's like it's a giant XYZ positioner with the
right. So this is different. This one is portable, and they can take it and set it up in stadiums without it being physically installed, where most of the venues now have bought their own it's not called FlyCam, but they bought their own and installed it in the stadium, and then the vendor operates it for them.
But you'll see this, I was indicating earlier that my love of sports usually is motor racing, and these straight line shots like this are very often the same kind of thing, because they'll chase cars down a straightaway. And it's a very exciting bit of footage for these kind of things.
And John, can you comment on the wireless link here? What kind of hardware is used for that, and what's the distance?
They use modems from a company called Teledesign in the Bay Area, and we're running anywhere from 19.2 to 38.4. There's a separate radio for the drive and a separate radio for the control in the camera. And then they've got they have a man that operates the movement of it down the rope, and then another guy operates the camera. So they've got 2 transmit modems, 2 receive modems, and they're all running off 12 volt, obviously. And we're just sending serial to it with, I forget the name of it. It does a packet check, so that if it drops packets, it'll just come to a stop. If it drops packets for, I think, a second.
Yeah, we have in all of the wireless things we've done, if we will tolerate a couple of dropped packets, and we're usually running 30 packets per second, so it's not crazy fast at all. Like, it kind of goes along with the television 30 frames per second standard. But we made a decision for safety. If a transmitter goes offline and the motor is running, we have these emergency procedures. So if we lose communications with the master, then we go into a shutdown mode and bring the device to a quick and safe stop. And we've done that on bunches of projects.
Yeah, when they go to these venues, there's a lot of frequency contention, and they actually have a frequency coordinator that assigns the frequency that they're supposed to be on. But sometimes other vendors will jump on that frequency by mistake or whatever, and it will really affect the operation, or it used to, before we set this up for them. But so in terms of safety and somebody else getting on their frequency, the previous units they had would try to run away on them. And of course, that's not allowed anymore at all. And they were trying to do it on 2.4 gig, but now they're down in the 460 megahertz range, somewhere in there, with assigned frequencies. And they just adjust the modems with a program and set it to the frequency that the stadium gives them.
Looks like you can talk to the modem from your PC. I guess there's a lot going on in that box.
Can you use spread spectrum at all to kind of not be in any particular place?
I know about that technology. I know they're not using it because they're old school. All these sports engineers are old school and they like the frequencies they've been using forever. So
Yeah.
while that's available, probably they're still old school and stay with a set frequency per vendor.
And for those high bandwidth video feeds, like probably 4K, you need a big fat channel that probably doesn't move around.
That's correct. And they, the company that actually does the video, if it's ESPN or whoever, they will give this vendor a video transmitter. So that's a third link. And that transmits directly to an antenna somewhere on the stadium that converts it back onto coax or fiber and then to the production truck. So that's even a completely separate link that's running the 4K video down. So 3 links, and the camera's on a stabilizer. So even if there's wind or shake, the camera's completely stabilized in it's a Ronin 2, which is a broadcast level camera stabilizer that can hold a good amount of weight.
How much does that whole tram weigh? Must be like 20 pounds or something.
No, there's about 50 pounds on there with the batteries and everything. I don't know if you've seen those batteries, but they're about 8 pounds a piece, and he's got 4 of those.
Whoa, wow.
Plus the payload. So
you guys have to show up at the venue like the day before and reel out all kinds of steel cabling and get it hooked up to where it needs to be and all rigged, and then you can set that thing on there.
Yeah, they get there 4 days in advance. And it's actually synthetic rope. It's not a wire cable. And it's got like some ungodly amount of tension that it'll carry.
Oh, yeah, I've heard about these materials.
Yeah, it's rated for 10 times the weight that he's actually holding, or 20 times or something, he told me one time. But there's 2 safety cables, and then there's the 1 drive cable. So even if 2 of them break, they still have the rig held up by 1, and 1 will hold, like I say, 10 or 20 times the weight. So he's got a nice safety margin too.
So the drive cable, does it pull that thing back and forth, or just, does it mechanically pull it around?
The motor is actually on the sled. So the ropes are all stationary.
Oh yeah.
There's a pull attached to the motor, and it's just driving it down a stationary rope. His original rig, the actual rope moved around a pulley like a clothesline would, and then he had the motorized reel down on the ground, and it went up around pulleys. And so I say this really simplified the application.
It consolidated all the moving parts into one piece.
Exactly.
You don't want that to fall on anyone's head, do you?
No.
Yeah, there was a race 5 or 6 years ago where one of these did fall. And thankfully it fell on the track. It didn't hit anything, but sadly, because a rope came down, a car drove over it and it wrapped itself around the axle and tore the wheel off.
Oh no.
So that team was really unhappy with all the damage to the race car. But, you know, I mean, thank goodness, you know, here in this case, I mean, you see from a safety standpoint, this could be crazy. I mean, you're flying it over human beings. And as John, 40 or 50 pounds, if that comes down.
They won't let drones fly over crowds like this, but they will let these cable cams.
And is there another one of these setups on the other side of the stadium too?
No, they just had one here. Some venues, they'll run 2 of them. Like on a golf course, they'll put one usually on the 9th hole and the 18th hole, where they have a lot of water features and stuff like that. You'll see them there. They've done a little bit of MMA and WWE. And of course, they've done movies and stuff like that where they want to get this kind of perspective from the camera.
Man, how much does it cost to have you guys come out and set this thing up for a day of use?
You know, that's something I don't know. I don't know how much he charges for it. I'm sure it's rather expensive. I know the Rose Bowl, he's been doing it for 20, 30 years now. And they insist on that shot because his shot is the shot of the outside of the stadium, and the camera flies by the Rose Bowl logo on the outside of the stadium up to the stands and peeks over into the field. And they only use it on commercial, coming back and going to commercials. So they're spending that money just for that.
Wow.
You know, John does all this, you know, machining and you know, well, he makes his own circuit boards too. I do tease John a little bit because he wants to, because he's got specialty clients and he's making small quantities. So, you know, he's using, you know, P1 40-pin dips. And, you know, we put everything in socket so it's easy to service. But that's why I went to visit him a few weeks ago because we were wrapping up our other project. And I deliberately took my edge board with me to say, look at this, we can plug it right in. How nice is that? And we get a giant amount of horsepower. So, you know, it depends on what John's clients want to do, but I'm, you know, from the time I started really getting into the P2 when it's, you know, in the spring when you had, you know, Spin 2 available chip and I was able to do that, because some of the most complicated code, or not complicated, well, I guess complicated and sophisticated code I've written is for John. You know, we had a project, I hope I can talk about this, John, I think it was a simple one, where it was 4 camera controls over that high power XB. So there was a base station with, you know, that you could control the camera and then you could select which camera was talking. And it was, I think it was for, wasn't it for a minor league baseball field?
Yeah, it was a guy in Texas that was doing play-by-play and switching cameras and streaming it live all by himself.
Multitasker.
Yeah. I wonder if you could build a kind of system where you put like 100 cameras all around the stadium looking inward and then correlate all that and then just synthesize any view you want with no moving parts.
There, you know, there is this thing called photogrammetry or something where they, you know, in fact, I made a circuit board for a friend of mine in a local special effects shop that I got to finish up for him, that they have a booth that's about 10 feet in diameter and about 12 feet tall that has 50 DSLRs mounted in it at even spacing. And then they'll put an actor or a model or something in there and say, hold still. And then they press a button and all the cameras activate simultaneously. And then they download those images into a program that can turn those 2D pictures into a 3D model of the actor.
Wow.
Sounds like the Matrix.
Well, yeah, there was effects in the Matrix called Bullet Time, and that was really kind of the beginning of this, where they took a bunch of simultaneously or specifically timed images so they could do these synthesized camera moves. But they did that. They took a bunch of still pictures in offset cameras versus physically moving a camera.
Yeah.
Right.
Yeah, so we've done lots of fun camera control stuff in some not, you know, so like the high-end broadcast cameras that are being used in these applications, like I was saying, that the lens control is a voltage thing. So the focus and zoom is voltage controlled. So we take voltage coming back from them and then since, because isn't it go -5 to plus, what is the voltage range to the lens?
5 volt is idle, 7.5 is zooming in, 2.5 is zooming out.
Yeah.
And then focus is the same way.
Yeah. So we're doing, you know, things with op amps to keep everything so we can, you know, so we can just have a simple value. But in the P1, we did really kind of a simple thing where we used a variable, a digital potentiometer as a DAC. And then we, you know, again with the P2, I was, in fact, I was telling John again this morning with the P2 DACs are so easy to set up and just send a value to. It'll simplify our code, honestly, and the circuit design. It'll just be an op amp and a resistor value choice. Because like on the motor drive is in that rig you just showed, John, is the motor drive similar to the one we just did where it's a 0 to 10 volt out?
No, that one's got a, shoot, because it's a DC motor. And I think we were going to do serial. Maybe you're right, John. Maybe that one's a 0 to 10 too.
But we've done in the projects that John and I have worked on together for his clients, you know, we've done straight, you know, PWM control. And there was another engineer that worked with a former, not former friend, but a friend of John's and mine who sadly has passed away, who had created this analog circuitry to monitor motor current. So we knew if we were if we were having a problem with a snagged cable, and we could goose a motor. So we've done very traditional stuff. And then the project that we just did had a 0 to 10 volt value. We've done serial control, so other things, but it's all has to do with controlling motors, and it's not convenient for me to grab, but is that stepper you were telling me about?
That's the motor that's driving the video that we just saw.
Oh, yeah.
So you can put an encoder on the back and put the pulley on the front. So it's a pretty beefy motor.
Yeah.
Made by Amp Flow. It's probably from China, but it's a nice beefy motor.
Now that's a motor.
We've done things, so people that have video cameras may have noticed a little, you know, I don't know if it's an 1/8 or 16th inch jack on the camera that has a little funny circle with an L in it that is for, anyway, it's a Sony port called LAN-C that is a half duplex open collector serial port that you can talk to the camera. So we've done that on several projects where, you know, in fact, I think on wasn't the project for the baseball thing had LAN-C control on
the
ends. Yeah. So we were on the base station, you know, you could control things, and then it was a switcher too. So you selected which camera you were talking to. In that particular case, we were using, I think, 900 kilohertz, or what was, they were XBs. They were
the XB, 900 megahertz XB.
But we ended up putting the addressing in the packet. So the packet was kind of a global broadcast, and then the cameras would pick their address out of the packet and do the response. So we kept it kind of simple and clean, but that gave us the ability to tell all cameras simultaneously, okay, shut down or turn on or do whatever by using that kind of, instead of having, I've done some XB stuff like with the laser tag I mentioned. In the laser tag, whenever the victim is hit, it configures the radio address to go to the shooter. And so it's only talking to the one. Anyway, so yeah, John and I, it doesn't seem, I mean, gosh, we've been doing these things for a while.
Yeah.
Just a big, long list of fun projects like this that we've done.
I've got a bunch of them, Ken. So if you're up for it, you know, we did one for the military where they simulate the jump lights out of paratrooper airplanes and the P1 and that program. I probably have forgotten a bunch of them, but if I look back, I'll give you a list of them and you can decide which ones you think are interesting for.
I would be absolutely thrilled to do that.
Yeah, interestingly, Ken, that jump simulator timer simulator, that used a Mac 7219. We just covered.
And John, you did some LAN-C in the OBEX, right?
Say again, Jim?
You did some LAN-C stuff in the
Yeah, it was, I shoot a little bit of video, and I've saved every camera I've ever purchased, so I have too many cameras. But that LAN-C protocol is really kind of nice. It's very simple. It's interesting from a serial standpoint, since the topic of today was serial, because the way LAN-C works is that the device, in this case the camera, it's going to send a status packet that is 8 bytes. The first 2 bytes, though, are always FF, which means they have a start bit, and then all of the bits are set to 1, which means that the the other side, so a controller side, in our case, the propeller, can stomp on those 2 bytes, which the camera is monitoring. So that's how you send commands into the camera. So it's an odd thing. The camera actually creates the start bit for the byte that we're going to send back to the camera. It's a peculiar thing, but it works. And John and I have used it a bunch of times in camera controllers. And with the propeller, it's very, very easy in assembly to synthesize that, because it's a 9600 baud connection. It's really slow. But you can see the start bit coming in from the camera, and then you know the timing of everything else. And you send the 2 command bytes in, and then the rest of the data you collect from the control side. So that'll tell you, like the battery level. That's what we've mostly used it for, battery indication and on and off and other things. So, but it's an interesting strategy that they did, where they said, hey, here's an 8-byte packet. And if you want to tell the camera or the device anything, stomp on these first 2 bytes and we'll pay attention to that.
Interesting. I gotta go shut the compressor off.
Okay, Jim.
John, it's really nice to see how all the work that JonnyMac is doing will apply to John Huffman work in the future with the P2.
Well, yeah, you should see, and in fact, I've known John for a long time, and we were, because of that silliness with the CRC, and it really dogged me for a while. John was being very patient with me because until I saw it, I couldn't see it. And then we wanted to finish up, and he had the gear, because he has a nice machine shop. I mean, he makes all of this beautiful metal work. And, when I was up there, he was doing a non-kind of movie-related project. It was this amazingly beautiful machine with stainless steel and aluminum and lots of interesting stuff that was going on. So, we both love the art of technology. So John with his metal work and the stuff that we do, and me with the electronics and stuff. And, together we've created some really neat projects.
I wanted to put a propeller in that one, but they wanted PLC instead.
Thanks for trying. Well, you might want to join us for the XB talk too in 2 weeks, John.
Yeah, John has lots of experience with that.
I love XB
quite a bit. Yeah, me too.
I just don't know why you guys stopped selling antennas for them.
That's a good question.
I have to buy them elsewhere.
It's probably asleep in the marketing people discontinued them. Well, should we wrap it up? Any final questions for JonnyMac while we got his attention? John, I just want to thank you again, and also invite people to go over to your johnmcphailin.com website and make a deposit in the bank of JonnyMac, because every day that you're not working for somebody else, you're working for all of us. And this is incredibly valuable. And I know that in March, we'll lose some of your attention because Formula One will start up on Sundays. Then you'll be ruling out Sundays for coding.
Yeah, I do pay attention to racing. It's something because it's a high technology thing. I love auto racing. Yeah, this is a final story. I love the Indy 500 too. In fact, the lady that cut my hair today, she's from Indianapolis, so we were talking about the race. And when I was a little boy, I made a crystal radio, and I listened to the Indy 500 on my crystal radio while my family was watching it in the house on TV.
I can picture that.
Yeah. Well, luckily we had a very long backyard, so I had this enormous antenna.
It's funny that people are going to be satisfied with whatever level of stimulation they get. I mean, now we expect to see lots of things and get lots of information, but back then, listening to something that you couldn't directly see, that was just being verbally reported over a little earpiece, was the big deal that was enough to completely occupy a person.
Yeah, but it was on a radio that I made.
Yeah. Well, that's more meaningful than what mostly goes on today.
Exactly. Well, that's Yeah, I think a lot of people in chat know Rick, and I probably told this story more than once. When he was having a Hanukkah party, and we were kind of showing people the shop, and people were very excited, ooh and ah, and, because Rick has some really neat things in his shop. And he turned to me and he has this kind of wry smile, and he says, the great thing about our lives, if we want something, we can make it. And he was right. And then I thought, I want to help, and this is one of the things that Parallax does so well, is inspiring children. We want children to be makers of technologies, not just users and consumers of technologies. And so hopefully, that's my push, is, trying to make the Propeller, approachable and fun and easy and yet very useful to do real world things. And, when you see things, and John, thank you for sharing and stuff, because, it's easy to talk about stuff in the abstract, but here, John is, doing these amazing things with metal and electronics, and, from on the TV, we get these beautiful aerial shots. It all comes together, and that's hopefully somewhere along the line, there's a kid that sees this and says, hey, I want to do that. And then they start to learn, whether it's learning how to deal with metal like John does, or do electronics and programming, which John also does. We got to find ways to get kids past just buying the latest Xbox.
Well, we have one kid so
Counting
far.
my age.
We have Kevin R in our P2
Kevin.
forum, and he's 10. So we have one token youngster doing cool stuff.
But remember Ken, when we used to do, and I lived in Dallas and they had it there, but IBM used to do this kids camp in the summer, and I would spend a day, you'd send me a bunch of bobots, and we would teach 30, underprivileged young ladies who lived in inner city Dallas, they were all 10 and 12-year-old girls, how to program robots, and they loved it, and they did amazing things. And we've got to find ways to keep kids inspired, especially after all of this nonsense with our shutdown. And for those of us in California, living in the dictatorial state of California, and what we've been through in particular, it's bad. We got to get kids, get them some fresh air, get them out into a big shop like Jim's. Holy cow, I'm jealous of your shop, Jim. Every time you change the camera, I'm thinking, I need a big space like that to work in. John, well, a really great shop too. I was just in his shop.
There's another 5,000 square feet over there.
Man.
Yeah.
John,
I might have to move.
We're talking about robotics and kids. How many of you know of US First and the First Lego League and the various different age ranges they have? They have like 4 different programs for STEM education for young student teams.
Well, Ken, wasn't the first robotics controller based on the stamp?
Yeah, it had a BS2 interpreter in it for about 5 years.
And Rick, his kids went to a local private school, and they have a very big program with FIRST robotics. They do, and then Rick, being a machinist, he's able to help them, but he's very good. He said, look, I'm going to show you how to build something, then you're going to build it.
Yeah, the reason why I mention it is I spent 9 years as the head referee for Colorado for First Lego League. This is 9 to 14-year-olds building and programming autonomous robotics to run courses on a 4x8 table and accomplish things with sensors and actuators. Then they go from elementary to high school. In high school, they're remote control instead of autonomous. They have a 30-second autonomous period, but all the rest was remote control. Kind of fascinating that they went that direction. So our younger kids are doing autonomous robotics.
Yeah, it's crazy, isn't it? I mean, obviously there's room for both. We need to have, the ability to steer a robot into, you look at search and rescue robots, those kind of fascinate me. And, you need to be able to steer them in, but then they have to be able to do, situational things. That's where reading sensors and understanding their orientation and, those kind of things is really critical.
Absolutely.
And I think, if we get them young, we have a chance. That's the thing. So I given my age and there's no kids in my neighborhood, because I'd almost want to go hunt them down and say, hey, come let me teach you electronics. So let me teach you how to write some code. Some fun, I promise. But then
I'll tell you.
I live in California, I'd be arrested.
Yeah, really. I think that's one of the things that kept me motivated for so long doing it is I'd travel the state doing 5 or 6 competitions on weekends every year. And there's nothing more exciting than seeing teams, 5 to 10 people on a team, and something like 40 teams every weekend competing. And seeing these young kids all excited, enthusiastic, their teachers, 9 to 14-year-olds, as I said, that was one of my best weekends. I was physically tired every weekend, but they were by far the best and most exciting to see that happen.
Yeah. I have a son who's grown now, but there's nothing, to me as a human being, nothing better than seeing the joy of a child who feels a sense of accomplishment. That's an amazing thing.
Absolutely.
All right, guys, I gotta go.
Hey, Jim.
Gotta take some cancer.
Okay, so have a good evening, Jim, and we'll end now the JonnyMac presentation. I think.
Thank you, everybody. Appreciate
thanks for coming, everybody.
And anyone who wants to can hang on while Ray asks Chip questions about configuring Smartpins.
Okay, I'll hang out.
Cool.
All right, Chip, I'll make you host at this point.
Okay.
Thanks, Ken.
Yep, thank you very much.